we're saying that the moment of a force, if you have a system pivoted here, and you apply a force on that system here, this force is F. The moment of the force is always the product between the force and the displacement, the perpendicular distance. This distance must be perpendicular. X. So the moment of this force is simply F by X. Simple. This moment is a particular type. This moment in this direction, because it turns the system this way, we can call it clockwise moment. All right? Now, if, however, we had another object, let's say we had an object like this, and the object was really resting on a surface. The object was really resting on a surface. Like on a table. Like so. If we exerted a force on this object, anywhere, like let's say here, this force will have a turning effect. And clearly, that turning effect is going to turn this thing in a clockwise direction. Just like this is clockwise. Now, in turning it, we're assuming it doesn't slide the force. In turning it, it is going to pivot about this point. That would be the pivot point. So the object, if I were to put this slightly different color, if I were to put this, it's going to pivot like that. That's what I mean by turning clockwise under the application of this force. So the clockwise moment of this force is, again, is the force multiplied by the perpendicular distance. This force is acting along a line called the line of action of the force. This force is acting along this line. That's called the line of action of the force. It's an infinite line, if you will. The line goes backwards and forwards, an infinite line. This force is lying along that line, acting along that line. The moment of this force, which I shall call F2, the moment of that force is, again, the force multiplied by the distance, and the distance in this case is the perpendicular distance, the distance from here to here. That's what the distance is going to be. All right. So you always have to find the distance that is perpendicular to the line of action. This is a line of action. The distance is always perpendicular to the line of action. And if that distance is F, the moment of this force will simply be F2 by X. The clock is going to be clockwise, and it's going to be F2 by X. Right, that's the moment of the force. Clear on that. So that's moments. You have clockwise moments, you have anti-clockwise moments. That's the concept. If I have another example, if I have, let's say, a wheelbarrow, which have some kind of load here and a wheel, this wheel would be where the pivot is. And if this weight inside the barrow is acting down, the moment will be equal to the W multiplied by this distance, the perpendicular distance between the force, which is the weight in this case, and that line of action. That's this perpendicular distance, pivot on that line of action. And that will be your distance X. So that's the first idea to remember what clockwise moments are. Anti-clockwise moments is just the opposite direction. The next thing we need to know is the principle of conservation of momentum. Sorry, the principle of moments, where when a body is in equilibrium, the clockwise moments about any point clockwise moments about any point must be equal to the anti-clockwise moments about the same point. That is tantamount to saying, okay, if we have a book here, and if you have a fight in Tunapuna, and Kevin is pulling the book in this direction with a force of 8 Newton, and Alicia is pulling the book in the opposite direction with a force of 6 Newton, we know that this book is going to move. The book is going to move in the direction of the larger force. In order for this book to remain at rest, what we need, obviously, is for Alicia to exert a force that is equal to Kevin. And therefore, these two forces will cancel, and the book will remain at rest. In the same way, if we want something to remain balanced, the clockwise moments must be equal to the anti-clockwise moments. Another point I failed to mention is we had defined another concept called the center of gravity. And what is the center of gravity? It's a point where the entire weight of a body acts. It's called the center of gravity, right? So for example, if this was a regularly shaped object, its center of gravity would be in the middle here, somewhere around here. And this center of gravity, there's a weight acting down. And this weight will provide moments that is anti-clockwise. And when this force tries to turn the system clockwise, the weight tries to prevent that or oppose that rotation. So this is anti-clockwise moment, this is clockwise moment. And when a system is to be in equilibrium, the clockwise moment about any point must be exactly equal to the anti-clockwise moment about the same point. So that's a quick review of I'm going to save this though. File, save. I'll save it in the same Dropbox folder on mechanics. So you'll have access to the actual file. You have access to the actual file that I just created. So that is, I can clear the file now. That is the revision that you needed to know in dealing with moments, that's a series. So if we are now asked to do questions on moments, any question? For example, this question here. Let me just take it from here.
Okay, start.
And I can drop it right here. Just make it a little smaller. Right, so that'll work now. So the question is, simple question. Patrick and Patricia show their class of magical balance and act. They both start on one side of uniform. Now, once they use the word uniform, what does that tell us? Once they use the word uniform, 6-meter plank. Immediately, the word uniform tells us that the center of gravity the word uniform is telling us that for this 6-meter long rod, or plank, the center of gravity is 3 meters, right? From the end, that's the first thing. So if this is 6 meters long, exactly at the 3 meter mark, the weight of the entire plank is going to be acting. Right. Patrick sat 1 meter from the pivot. So that's Patrick, 1 meter from the pivot, located 0.5 meter from the center of the plank. So this pivot is located 0.5 meters. So if this is from here to here is 3, from here to here would be 2.5, right? That would be 2.5. Just write it here. Patricia sat 0.5 meter from the pivot. So Patrick was 1 meter away, Patricia was 0.5 meter away. Label a W at the point where the weight acts, right? So I already got that. All right, label a W at the point where the weight of the plank acts. That's 1 mark. Calculate the weight of the plank. Now, if this plank is balancing, it means that the clockwise moment about this point must be exactly equal to the anti-clockwise moment. And we're seeing that there are actually 2 anti-clockwise moments. There's an anti-clockwise moment due to Patricia, right there. And there's also an anti-clockwise moment due to Patrick, right there. So we have to find these 2 moments because they're both anti-clockwise. And we have to create an equation where we equate them with the clockwise moment. Now, for the W, the clockwise moments will be W, the force again, from what we just saw. It's the moment of this force is this force multiplied by this distance. So that will be, for the clockwise moments, it will be W multiplied by, I'll put a dot for multiplication, multiplied by 0.5. And that will be equal to the sum of the anti-clockwise moments. There are 2 of that. First of all, you have Patricia's weight of 400 multiplied by 0.5. We have to add that to Patrick's moment, which is 500 multiplied by 1.0, because he is 1.0 meter away. He is he is 1 meter away. From here to here is 1 meter. So we have to use the 1 meter here. While Patricia, she's 0.5 meter away. That's why we're using the 0.5 with her weight. And W is 0.5 meter away. Again, that's why we're using that. So it's pretty simple to solve this question to be able to get the value of W. So that's 200, that's 700 over 0.5. And the weight of the plank then should be 1400 newtons. All right, you okay with that? Any questions there? No questions, going once? No questions at all. So we just got that 4 marks, get the weight of the plank. If Patrick sat alone now, so we're moving Patricia. If Patrick sat alone, calculate where he should have to sit in order to maintain this balance. So let's draw a little diagram to help us here. Again, this is the plank. And again, the center of gravity of the plank is located at the middle of the plank, which is 3 meters from either end. So that's where the center of gravity is. So that's where the weight of the plank is acting. We also know that the pivot is situated 0.5 meter, just like this, 0.5 meter, the pivot is here. So that is 0.5 meter. And they want us, clearly we have to move Patrick. Patrick can't sit here because Patricia was helping him to balance the plank. Now he has to do it alone. In order for him to produce a larger moment, he needs to move further away. He needs to move some unknown distance away. We don't know what the distance is, but we know his weight is 500 newtons. So in order for him to balance the plank, again, we don't know what this distance is. So because we don't know what it is and he's moved, it's no longer 1 meter away, we will call that distance x. So from this, we can see, again, applying the same principle, if this plank is to remain in balance, the clockwise moment, which is this force multiplied by this distance, the clockwise moment must be exactly equal to the anti-clockwise moment, which is 500 by x. Again, we take moments about the same point. So we really create an equation that 500x must be equal. Now, in this case, by working the question, we got this to be 1400. It's right there. We got this to be 1400. So we have to replace it here, 0.5 multiplied by 1400. Again, it is force multiplied by perpendicular distances. Force multiplied by perpendicular distance. So from here, we can work out what x is. X is 7 over 5, which is 1.4 meter. That's what x is. So this, Patrick will have to move back a further 0.4 meter. He was here, he was at 1 meter. He was here at 1 meter. He has to move back a further 0.4 meter to balance the plank. All right. So we understand that moment question. Any problems with that? Anybody would like to, any clarification? We finish the entire question now. If you have no clarification, you can just type in the chat window yes or no. So I will get feedback to know whether I'm moving too fast or too slow. Or if you need any clarification, you can just unmute your mic and see. You can answer directly. Nobody talking to me. Anybody hearing me?
Yeah, I hear.
That's Kevin again.
Yeah.
Anybody else hearing? All right, everybody seems to be good. I got a few responses from Keon and Fabi and all right, Said and Felicia. Okay, you're all good. So that's clear. I can clear this now. Again, I could probably save this file, save as in that same folder. I will call it Patrick balancing or something like that. Okay, so I'll clear this again. So we just did a moment's question. Again, we're going to touch different topics. We're not going to stay on any one topic. So having done a moment's question, I'm not doing this right now. Now, by the way, what I was doing this morning in preparation for the class was, you're familiar with this handout, right? You're familiar with parts of this handout, at least. These are the other moments questions. You would have gotten them during the course of the classes and so on. You would have gotten these questions. What I've been doing is I've been saving solutions to the questions. So for example, this is a solution for this question here. Question 1, there's an entire solution laid out so you can refer to this. I will save this to you in Dropbox so you can access this. Several of the questions. You have the question here. You have the detailed solution to the question. I haven't been able to do all because it's a very time-consuming thing. So, but I'll continue working on it. This one is an interesting moments question. I suggest you all take a look at this if you have to do moments for the end of term exam. I suggest you take a look at this question. It's a 1990 question. Write down the reference somewhere. 1990 paper 3 question 6. It will be in your past papers, and it will be in this file that I'll save for you in Dropbox. The next topic I'm going to do is kinematic motion in straight lines. I think we did this question last night. So I want to do some other questions. All right, so let's take a look at a couple of these. Somehow I felt we worked this in class as well on Thursday, did we? Did we work this in class on Thursday? Anybody would like to tell me that?
Yeah, we did.
We worked this in class, yes, it looks very familiar. So let's take a look at this one here. This is 2006 paper 3. Again, I will just I'll just copy this whole thing here. I'll take it across to my work and let's see if I can just take it across like that. All right, yes, it's here. All right, whatever. All right, so state in words Newton's 3 laws of motion. State in words. And that's the 8 marks. What is Newton's first law? A body continues, the first law. Right, a body continues in a state of rest or uniform motion, a straight line provided that no net force acting. And the second law says that the net force is directly proportional to the rate of change of momentum. And the third law says that is the one that goes right. So those are the 3 laws. Once you start talking Newton's 3 laws, we should also mention the other law that we discussed, which is what's the other law of motion that we explained that is no longer valid. Anybody like to tell us what the name of that law is? What's the name of that law? Whose law? Type it in the window. These are Newton's laws of motion. There's another chap who had a law of motion that is no longer valid. Don't all jump at once. His name was, starts with A. Come on. Yes, Davi. Aristotle. Well done. Aristotle. All right. Aristotle had a law of motion in which Aristotle said that when a body is moving, it needs a force when a body is moving, it needs a force to keep it in motion. All right, when a body is moving, it needs a force to keep it in motion. Unlike Newton's first law, Newton's first law says a body continues moving provided there's no net force. Aristotle is saying when a body is moving, it needs a force to keep it moving. Sorry, let me just not do that. Yeah, when a body is moving, it needs a force to keep it in motion. And what's the other part of that? That force is directly that force is direct proportional to the velocity. Okay, we good? That's called Aristotle's theory of motion. So it's different from Newton's law. It's no longer valid because Newton's law came and superseded it because Aristotle wasn't really aware of the concept of friction. So that's no longer valid. All right, so we understand Newton's three laws and we understand Aristotle's law. Now to the question. A Boeing 737-800 aircraft accelerates from rest to take off at 300 kilometers per hour, 25. All right. Now, I went through in class the other day the conversion. How do we convert from meter per second? What is the conversion factor from meter per second to kilometer per hour? I pointed out to you, sorry, the other way around, from kilometer per hour to meter per second. I pointed out where it was in your handout last day. Well, not last day, but the session before that. How do we convert from kilometer to meter per second? What's the factor? That's right. Multiply by 10 over 36. Nice, well done. If you want to make this conversion from here to here, you have to multiply by 10 over 36. Right, and in class we showed y was 10 over 36 because a lot of people didn't remember y. I suggest you go back if you don't remember, 10 over 36. So 300 kilometers per hour, if you multiply by 10 over 36, that's 3,000 over 36, and that will be 83.3 meters per second. Double check that. 300 by 10 divided by 36 equals, yeah, 83.3. That's in meter per second. So this aircraft is accelerating from rest. So if you want to visualize the motion, the aircraft was at rest and was accelerating. Oh, sorry. It was accelerating, and the final velocity was 83.3. And this happened after a time of 25 seconds. So they're asking us, first of all, to calculate in meter per second squared the value of the acceleration, assuming to be constant. This is a graph of velocity against time, of course. And we know that when you have a velocity time graph, the acceleration is really the slope. And the slope of this graph is rise over run. It's rising by 83.3. And the run here is 25. And from here, we get that the acceleration is 3.3. And that will be meter per second squared. So we get there. That is the acceleration. Continuing, the aircraft has a mass of this. Now remember that although this is a statement of Newton's second law can be reduced to F is equal to ma. Can be reduced to F, but that's not the law, as I keep telling you. This is not the law, right? This is just how you can take this statement and convert it to this, all right? F is equal to ME. The aircraft has a mass of this. Two identical engines provide a thrusting force. Calculate the magnitude of the thrusting force needed to give the aircraft the acceleration. So again, we know the mass, which is 6 by 10 to the 4. And we just got the acceleration, which is 3.3. So from this, we can get the force. Because this is the acceleration that results, this is the force that is needed to push this heavy plane. And this gives us 11 by 10 to the 4. And that will be in newtons. I'll double check that. 6 multiplied by 3.3. What rubbish. Hold on. Plus. 6 multiplied by 3.3. Yeah. No. That's nonsense. Let me double check the calculation. 6 trees, that can be 11. Obviously not. Let me do that calculation. 6 PE4 multiplied by yes, it's 2 by 10 to the 5. 2 by 10 to the 5, not that. Two. 1.9999 whatever. 2 by 10 to the 5. So that is the total thrust, right? This is the total thrust. But remember, you have two identical engines, and they want the thrust of each engine. So the thrust of each engine would be simply half of this, which is good. The thrust calculated in 1 is a theoretical value, suggests a reason why if this thrust is applied in practice, it would not provide the expected acceleration. Well, what we're forgetting about in this calculation, we are forgetting about air resistance. And the first calculation part 1 is a theoretical, suggests a reason why if this thrust is applied in practice will not provide the expected acceleration. Because
and sweep your room and take out all the bottle and whatever. I ain't gonna sweep no I'm thinking of not tonight.
because some of the forces needed to overcome friction, right? So when you, I mean, let's look at it. You have the aircraft. You have the aircraft, and you're providing it with this force. You're providing it with this force. This force is the 2 by 10 to the 5 that we're talking about. And the calculation is telling us this would be sufficient, but we have forgotten about the existence of another force, frictional force and air resistance. It's never going to go away. The faster the plane is traveling, the greater the air resistance is going to be. So there's going to be a force here acting in the opposite direction to oppose motion. Right? Now let's give, that's the idea. So therefore, when you apply this and this is acting, you will have less, and therefore the acceleration would not be as high as 3.3. So if a question comes like this and they ask you, so what force would you need? You would need to know what this frictional force is. And let's say let's give this frictional force a value. Again, we finished answering this part of the question, but let's give this frictional force a value. Let's say it is 0.2 by 10 to the 5. With this frictional force acting, and if this was the first developed, the force, the resultant force that is acting on the plane will no longer be 2, it will be 1.8 by 10 to the 5. Why 1.8? Because you have 2 acting this way and you have 0.2 acting this way. So you have the resultant is the difference between these two as 1.8. And if this is the force acting, then the acceleration is clearly going to be less than the original 3.3 value. If, however, this is the force acting on an aircraft and you wanted to still achieve the same acceleration, you would have to obviously increase this. You will have to increase this by exactly 0.2 by 10 to the 5. And if you do that, if you do increase this by this value and this is acting in the opposite direction, you can again result in the acceleration of exactly 3.3. Right? So that's how these things work. Once the frictional force come on, it will work against the driving force. And the acceleration will be dependent on the net force at all times. At all times, it's dependent on the net force. You okay with that? Last part. The mass of the aircraft was increasing by loading additional passengers and luggage. How would this affect the time taken to reach takeoff speed? Now remember, the takeoff speed is 300 meters per second. Right? Takeoff speed is 300 meters per second. Once you increase the load on the aircraft, as the mass on the aircraft increases, what happens to the acceleration? The acceleration would get smaller. Once you increase the mass of the aircraft, the acceleration will get smaller. Once the acceleration gets smaller, if the aircraft needs this length of runway to reach the 300, if it needs that length of runway to reach 300 kilometers per hour, with this extra load, because the acceleration is going to be smaller, the length of runway needed will be greater. The length of runway needed will be greater in order to reach the same speed at the end, 300. Clear now? So that's the answer to that. The mass of the aircraft was increased. How would this affect the time taken to reach a takeoff speed? So if you are actually going to be traveling a greater distance, you're going to need a greater distance to reach the takeoff speed. The time would be greater. So that's the answer to the last one. The time, in fact, would be greater. All right, we clear on this question? Give me feedback. Any part of it I went too fast on? I got 1 feedback. And 2, 3, and 4, and 5. Awesome. All right, that's enough. Thank you. I'm going to clear now. Better put this again. So this is aircraft. And again, it's going back in the mechanics folder in Dropbox. And I can clear this now. All right, so that's 1 question on moments, 1 question on kinematics. We're going to go on for another 15 minutes or so. I have to go to mosque. I have to leave home by 5:30 to go to mosque. So Is there any, sorry, at this point, is there any specific question? Any specific question you'd like me to work that you know, in here? There are a whole set of questions. I mean, you all have access to a lot of questions. In 5, 4, 3, 2, 1. All right. What I'm going to do is, you see this file here with all of these questions is long. I can't imagine that you'll have time. It's really 70 pages long. Okay, 70 pages. It's a big file. I will eventually save it. The ones that I have solutions, I'll save it in that same folder. So that you can have.
Oh, good. I'm gonna do it. I can do it.
All right.
No, I can do. I can have my school clothes. Yes.
All right. Let me
Yeah.
do that.
Yeah, just a more to do and not to do.
All right. Good. So that was. Yeah. Energy. We did this question, did we? In class, did we do this question? This question? I remember doing it. I don't know if I did it with you all. No, we didn't do it. Okay, so let's talk about it. January 2015. One of the things that physics is concerned with is the study of energy. Forms of energy and examples. Two major forms of energy and one example of each. So we have mechanical energy. What is mechanical energy? Anybody would like to tell us what is mechanical energy in the chat window or audibly? What is mechanical energy? I want a participation here. What is mechanical energy? Anybody, what is mechanical energy? Hello? Ah, yes, Kevin. Well done. Alicia, well done. Yes, mechanical energy is the sum of the potential and kinetic energy of a body. All right, mechanical energy is the sum of the kinetic and potential energy of a body. So that's the first one. So we're going to continue with this. So we remember that, right? Forms of energy and examples. For example, we can talk about chemical energy. Chemical energy, the example of chemical energy. The example of chemical energy would be, let's say, petroleum. Right? Petroleum will be an example of chemical energy, or it could be the candle wax. You know, a whole range of things. It could be firewood. Right? All of these are examples of chemical energy. Another form of energy is, what other form of energy you want to use? Geothermal. And the example of geothermal is from hot springs or volcanoes. Right? The SI unit of energy is, of course, the joule. And define the SI unit of energy. 1 joule is equal to a force of 1 Newton acting of 1 meter. Right? So that's the definition. 1 joule is equal to 1 Newton by 1 meter. So now this part here. A bucket, let's make this a little bit bigger because I'm going to try to type the answers here one time. A bucket filled with cement of total mass 60 kilograms, total mass meaning the mass of the cement and the bucket, I guess, is raised vertically 150 meters from the ground to the 12th floor of a building under construction, which is example 1. Calculate the energy that was needed to perform this activity. Now, what kind of energy would the bucket have at the top? The bucket will have potential energy at the top. And we have to give it an amount of energy equal to the potential energy it has or gets. So the potential energy we know is equal to mgh. And in this case, it's going to be 60 multiplied by, let's see, insert symbol, sorry, insert symbol, multiplication, multiplied by G, which is 10, multiplied by H, which is 150. And from there, we can get our answer. I'm not going to work it out. So, well, I guess I have to work it out. 600.
90,000.
90,000. Thank you very much. Thank you for that help. 90,000. And that will be in joule. So basically what we're saying, because when it reaches here, it would have 90,000 joule of potential energy, we need to put in at least that much energy. We have to put in that energy in some form, in terms of a battery, in terms of electrical power to lift it. In some form, you have to put in exactly this much, at least. And this is assuming there's no frictional forces. As we saw in the previous question, if there are frictional forces, we have to actually put in more than 90,000 because we need to overcome the frictional forces. Continuing. If this activity takes 25 seconds to complete, calculate the power. From the time we see the word power, we know the definition of power. The definition of power is equal to energy over time. So it is going to be equal to the same 90,000 divided by the 25 seconds. And that is how much, Kevin?
I have worked it out as well.
It looks like 36 what?
3,600.
3,600. That's right. Thank you. 3,600. And the unit of power is the watt. So that's pretty simple. Straight application. Now the last part. If friction was present, what effect, if any, would this have on the power needed? And we just answered that as well. The power needed will be greater. All right, the power needed will be greater to overcome the frictional forces. So that's a pretty straightforward one. All right, we clear on that? Everybody's just straight off definitions, right? I mean, questions could come really creatively, but you have to know these definitions to be able to apply the creative concepts. The last question I'll do is this part here. This part here. Did you do this question yet? No? 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 Okay, so let's look at a basketball of mass 0.44 kilogram is dropped vertically from rest. So the ball is being dropped vertically from rest, meaning if it's at rest, it means the initial velocity is 0. I'm going to just clip this. Sorry, let's clip this so I can move it into where I could illustrate then. Okay.
So what year is this one?
2014, June.
Oh, thanks.
June 2014, paper 2. All right, so let's go again. A basketball of mass 0.4 kilogram is dropped from rest. When we say it's dropping from rest, we know that the velocity u, the initial velocity u, is equal to 0. That's what they're trying to tell us. 12 meters from the ground as seen. Calculate the gravitational potential energy as a ball at the point of release. Again, we know gravitational potential energy is simply mgh. Now, in this question, they're actually telling us that g is 9.8, which is the true value of g. So we're going m 0.44 multiplied by g, which is 9.8, multiplied by the height, which is 12 mgh. So we get our value for there. We wouldn't necessarily look at it. How much?
51.744.
51.7 I'll use. And that will be in joule. Did I say P? It's supposed to be, what nonsense. Energy. That is energy, or potential energy. That's what I meant to write.
So I could ask a question.
Absolutely.
For the gravitational, for the G, right? Why some of them you multiply by 9.8 and some you multiply by 10? Does it matter?
It does matter. Your default mode is 10, meaning if they don't tell you anything, you have to use 10.
Okay.
All right. This is normally what we use in CSEC. That's your default. It's normally in the front page of your past papers as well. But this question is one of the few questions where they're actually telling you to use the true value. This is the value used at A level. All right. And this is the true value of G, it's 9.8. But for some reason, they wanted people to use 10 because they figured 10 was easier to multiply. But everybody has calculators nowadays. So again, you know, it's just that kind of thing. So the true value is really 9.8. It's approximately 10 for CSEC, and it's normally used as 10 for CSEC.
Okay.
Right. The final, you have to calculate the final velocity of the ball on reaching the ground 1.56 seconds later. Now, what we have in this case, in this question, we have the initial velocity, which is u. That was 0. We know the acceleration is 9.8. The acceleration. We know the time is 1.56. And they're asking us to find the velocity hits the ground. Now, again, we have, this is the equation, the information we were given, and we have to use this to select one of the equations of motion. And the best equation to use would be v is equal to u plus at. And therefore, the final velocity is 9.8 by 1.56. What do you work that out? 9.8 multiplied by 1.56. What's that? $15.28. That's correct. 15.3. Verification. No verification.
Yeah, correct.
Okay, good. And that will be meter per second. So that will be velocity of the ball when it's just about to hit the ground. And then find the momentum of the ball when it hits the ground. When it's hitting the ground, the momentum of the ball, momentum we know is equal to, momentum is equal to the product of mass and velocity. So we got the velocity as 15.31, so it's 0.44. Multiplied by 15.3.
6.73.
6.73.
Yeah.
And the unit for momentum is what? Anybody? Kilogram meter per second. Okay. So we understand the question. We have no problems with that. Pretty straightforward stuff. I would try to create some more a worksheet, a sample worksheet. I'll share a couple of Cambridge past papers so you see what the Cambridge questions look like. But we have to kind of end now as we get ready to go to mosque. I'm sorry I started late, people. I lost track of time completely. And it's only when Alicia messaged me, and the phone was on silent as well. I looked at the phone, I realized time had gone. But at least we still got the hour in. I hope it was productive and fruitful. You understood everything. So